Okay. All right, good morning. Let us start. So, okay, do you have any questions before we start? All right. So, first, I want to talk about the lecture notes that I just posted. So, as I mentioned, this is the notes that I used when I taught this course before. And so basically, up to now, we did not use the notes because we just basically covered the basic Black-Scholes model, which is pretty simple and, like not much technical details. But, coming into the jump process models and, moving on to like exotic options and things like that, the materials are going to get more complicated and more technical. So I posted the note, but also will be used as a tools for referencing. So what do I mean by that? What I mean is, for example, when we will discuss things like the partial differential difference equation. And the derivation, as you can see, is quite, involved, right? And well, I could just copy this down, in a lecture and tell you, like whatever is in the lecture notes, but I think that's going to be a waste of your time. It's pretty boring. So what I want to do, right, is in the lecture, what you need me is to tell you the broad strokes, like the main ideas of what we're doing and why we care about such things. The derivation you can always find in more details, right, in the notes. And also, by the way, right, your textbook, Shrif, part 2, even though we kind of never reference it, is still in the background, okay? It's still important. But the point is, for example, right, with this note, I can just simply say, this is the partial differential difference equation, right? Theorem 3.2.1, for example. Take a look. The derivation, right, is above it. We'll discuss some details of the some main points of the derivation, but we will not, right? I mean, go through all the details. All right. I think is an important aspect of your training too, because you will kind of like in your line of work, you will need to read technical stuff, right? And the point of reading technical stuff is A, you shouldn't be afraid of it, and B, right, you should be able to tell the main points, why you need the technical details, where you use it, and how to separate, right? Things like just justification, technical, right, calculations versus, right, some result that can be used. Okay. So again, like working through the notes, knowing how to pick things apart, how to kind of select what's important, what's not, is again an important skill. Finally, right, you can access the notes during the exam. In other words, right, besides your one page of notes, if you take a look into this, class notes during your exam, that's perfectly allowed. Except, right, you need to know where to look. Okay, I mean, like sitting there and browsing through the whole notes, searching for something, is practically, I guess, useless. Okay, because it's really big. It's like looking through the textbook for some details. So you need to know your materials anyway, right? And of course, the table of contents is up here, right? So, but you need to be able to kind of be familiar with the concept before you can use it. All right. And like I said, the notes cover way more materials than I intend to teach even, back then. Like now, right, I even want to simplify the process even more. So, some of the stuff we will kind of skip. So feel free to ask me, right, if there's something in these notes that, is not part of the class, or, something that you're expected to know, for example. Okay. All right. So give me a moment. All right. So to continue with where we left off last time, somehow my notability is really slow. All right. So last time, right, we were discussing, Black-Scholes model, right, with jump component. And to be strict, right, it's really not Black-Scholes model, because Black-Scholes model does not have a jump component. Okay, I just want to give a name to it, and then it is just like Black-Scholes model anyway, so I give it that name. But if you hear Black-Scholes model in practice, right, obviously people don't mean the one with the jump component as by default. But anyway, right, so the model is this. This is the physical model. So what you need to know, right? For example, first of all, what is the formula for ST? Okay. What is the explicit formula for ST? B is E minus RT ST a martingale. Why or why not? Okay. And C, possibly some kind of distribution of ST. D, simulation of ST, right? How would you simulate this? So that's just the basic model, right? How working with the model implies that you know how to do these four things, for example. And I could ask you a question in any of these four, and you would be comfortable telling me what they are. All right. So we'll go back to this, right? But in terms of pricing, then what do you need to know, right? Pricing means converting, right, this physical model to a risk neutral model. In other words, right, the risk neutral version looks like this. That's a risk neutral version. So you need to know A, right, the connection between this and this. So basically, what is the change of measure kernel? Okay, what is it? B, right? So just because you know what the change of measure kernel should be, doesn't mean that it exists, right? Or it's unique. So does it exist? When, right? When does it exist? Is it unique? So in other words, kind of equivalent to this kind of question is, what is the market price of risk equation? How many solutions does it have, right? Also, any important condition on the solutions, because for example, right, Well, you also need to know what are we solving for. So we're solving for the drift, right? The theta that's hidden, right? Going from here to here is adding a theta t, right, to the old bar motion, to a new bar motion. Also changing the rate lambda to lambda tilde. So the unknown, right, are the theta and the lambda tilde. But one special, right, restriction on lambda tilde is it must be positive, or at least non-negative, because it's the rate of a Poisson process. So there's some restriction on the solutions, right? And so if you have zero solution for the risk for the market price of risk equation, that means that the change of measure kernel does not exist. If you have one solution, then it exists and unique. If you have more than one solution, then it's not unique, right? But it exists. Okay. And so, of course, this also connects with the completeness of the model, right? Completeness of the model. And arbitrage free, right? Property of the model. So A, B, right? C is, again, right, the pricing equation. How do we simulate the price? Let's say of a call option, right? That's our vanilla call option. That's kind of like our testing ground, right? The easiest product that we can price. Any formula like Black-Scholes. Okay, these are questions that routinely you should ask, not just for this model, but for any model that you will see in the future, right? These kind of questions, again, you know, are related to, right, the basic pricing scheme that we consider. Okay, so let me just quickly, right, go through these questions. So let me call this 1, right? And let me call this 2. So for 1A, right, what is the formula for ST? The thing to remember is ST behaves just like the Black-Scholes model between jumps. So it is this, mu minus 1/2 sigma square times T plus sigma WT. This is your old Black-Scholes model. But at jumps, right, it picks up a jump with proportion 1 plus gamma, right? 1 plus gamma times the previous value. That's this right here, right? This tells you that it jumps with proportion 1 plus gamma. So therefore, it picks up 1 plus gamma jumps in product. How many times? NT times, whatever NT is, right? How many jumps that has happened so far. So that's the formula, right? And you can put them together as this. Okay, like that. B, is it a martingale? Is eta minus RT ST a martingale? The answer is no, right? Not likely. Why not likely? Because, you know, of the combination of because of the combination of the parameters, right? So look at, what do you expect for this, right, to be a martingale? Well, actually, not this, right? The discounted stock. So you should remember what is the effect of the discount. The effect of the discount is that it introduced a subtraction by R, right, onto a drift. In other words, if you were to do e to the minus RT ST, right, and look at the differential, then, right, what you have is something like this, mu minus R, right, and then e to the minus RT ST. T, this is unaffected, but of course you pick up the discount. Okay. We'll talk about, right? We'll talk about like basically what this does to the jump component. You basically still need something like a you need an EDOS formula for jump processes, okay, which we'll talk about. But basically, you can imagine that the discounting it also translates to the price of the stock. But there's a catch, right? The catch is that this is not a martingale, right? The Poisson process by itself is not a martingale. You need compensation. So two hurdles, right? First, the compensation. Second, the drift. So that's why we say it's not likely, okay? Not likely. I mean, I say not likely because God knows, for some reason, suppose that this term right here exactly equal to the compensation here, then that's the martingale. But like it's not likely because mu minus R supposed to be positive, so it cannot be compensation to begin with, right? But so the point is, right, asking this question is not asking you to prove, right, that it's not a martingale. You can do that too, but the point is more like, do you understand, right, what it means, what it takes to be a martingale, right? Also, you could look at from this explicit formula. You can look at it from this explicit formula, right? Because the same thing here. So the first approach, right, this right here is looking at the differential structure, You can also view it from the formulaic structure. In other words, because you have the explicit formula for S, you have, right, this again. Right? And here you see the same story that comes up. In other words, this structure right here should remind you of, right? This structure right here should remind you of e to the minus 1/2 sigma squared t plus sigma wt. Sorry, yeah, w, right? Which is a martingale, right? But of course here you have mu. So in other words, somehow mu must be 0 for that to happen. On the other hand, right, you have this structure. What should this structure remind you of? This structure should remind you of the other martingale associated with the Poisson process. In other words, right, it's e to the gamma nt, right, minus lambda times t times e to the gamma minus 1. Where of course, right, this gamma right here becomes is this term, the log, right? But you see, this is the compensation part that may match the mu, but unlikely because mu is positive and this is negative, for example, right? So all in all, understanding how, right, each of the piece plays a role in the price, right, in the component of the stock is what I asked you to be able to do. Any question on this? Okay, so yeah, question. When do we do? Oh, so you mean here, right, Cherry? Yeah, so I was saying that, so roughly speaking, right, you would expect something like this. Or rather, should I put the minus in here, right, like this. Okay. But so the point is that this is not compensated. So it's not a martingale from here. I hesitate to write down because one thing I did not tell you is something called the EDO formula for jump process. And so I did not put that part down explicitly. But the rough idea is it comes out to be something like this, or because the discussion centers around, is it a martingale, right? I just want to highlight the fact that whatever this is not compensated. So it's unlikely to be a martingale. Is that okay? But you see why I don't write down explicitly yet, because this formula requires you to go through another stage before you get to the formula. Yeah. Okay. So distribution of ST and simulation of ST, right? Simulation of ST, I hope you see it, right? You know what it is. So C code. But still, there is something interesting here, right? Two reasons. If you want to simulate the path of stock, then you need to follow this approach, or rather this, right? You need to simulate the path, meaning you store the whole path of the price there. Or you just simulate one value of ST. Okay, so let me talk about that a little bit. Two scenarios. Now that we're getting close to discussing exotic option, let's look at this. So, there are three types of options roughly, right? There's the vanilla type, which are, the European type. There's the exotic type, and there's the American type. Vanilla means, or European means, right, that basically you have something that happens at an expiration, and that's it. Exotic means it's path dependent. Okay. And American means you have a stopping time, right? Tau, right? A tau, an exercise time. So ignore this for now. Focus on these two guys in view of simulation, right? And I think one of your review session was playing around with the agent option. And you see, for one thing, from the point of view of simulation, if you want to price this, right? This is the price of the vanilla call. Do you need to simulate the whole path of the stock to do so? Do you need the path of the stock to do so? For this particular option. In other words, right, my question is something like this. Do you use this version? Well, I mean, like more like, the risk neutral version. But anyway, right? Do you use the explicit formula, or do you use the differential formulation? Do you see the difference between the two? I mean, they're kind of the same, right? But slightly different too. And the difference can come in here. Do you need the path of the stock to price the vanilla option? The answer is no. Okay, because only S big T is involved. So I know that, right? In my sample code that I give to you, I always go through the path of the Brownian motion and also simulate the path of the stock. The reason is it's a generic code. All right. If I give you a code that takes a shortcut, when we move to exotic option, maybe you do something wrong there. So I give you a code that may be inefficient in some case, but always works, right? But now it's time to point out the difference. The difference is this. Suppose that you want to price the vanilla, right? The vanilla call for the jump model, right? So suppose you want to price this, then the formula for ST, all right, in the risk neutral version will be this: S0 e to the R minus 1/2 sigma square minus lambda tilde times T plus sigma W tilde T plus NT times log of 1 plus gamma tilde. Okay. Sorry, NT plus gamma, 1 plus gamma. Okay. So lambda tilde is already here, right? For the rate of the risk under the risk neutral version. This is the Brownian motion under the risk neutral version. So, right, looking at this, what do you need? You only need two things. Need to simulate one single, well, one and single is the same, right? One normal 0t, one single Poisson lambda tilde t. Let's call this W, let's call this N. C, plug these into the above formula. Right? D, repeat, I don't know, let's say N times, add, and take average. I hope you know what I'm talking about, right? So basically, this formula only requires you to simulate S big T. So, and because S big T is this, all you need is to simulate W tilde T and N big T. So that's why because W tilde T is a normal random variable, and N big T is a Poisson random variable, all you need is to simulate two single random variables rather than the whole process. Right, in the coding language, you simulate one single value rather than an array. Yes, and then you just plug these values into their corresponding place, and then you plug this into here, right? And you repeat the process, and you add and you divide. You get that. The point is, right? In no procedure here that you go through this formula. Is that okay? Is that okay? And of course, recognizing this, right, saves you a lot of time, because suppose for each iteration here, you simulate the whole path. Imagine how long that takes. Basically, you just multiply your whole process by 1,000 times, at least. Okay. But of course, don't say that, well, then this whole thing is useless. This formulation, right? The reason is right? You can only derive this explicit formula from the differential form. But second, the differential form will be important if you want to price exotic option. Because suppose you were to price exotic option, And here, A, you need the path of W tilde T. And B, you need the path of NT. Unlike a single value of the random variables as before. And C, you will simulate the path of ST according to dST to be RST dt plus sigma ST dW tilde T plus gamma ST minus dNT minus lambda tilde T. Is this okay? So, and then of course, after you have the path, then you take the max and then you plug that in. But, right, so when I talk about the distribution of S big T, I was referring to the vanilla co-option version, right? If you were to deal with the exotic option, which we'll go in soon, the distribution becomes much more complicated. And I hope you see why, right? That simulation becomes like at least the easy universal language that we can put something on, like we can get our hands on at least experimentally the value of these options, right? Even though it may be very inefficient and not accurate enough. But one thing I want to highlight is the difference in terms of simulation too, right? In terms of getting a vanilla co-option, where you only need to simulate one single value at the end versus simulating the whole path. Any question? Okay. So now go back to the question of the distribution of S big T, right? What is the distribution of S big T? Well, again, let's write it down. S0 is e to the, sorry, S big T is S0 e to the R minus 1/2 sigma square minus lambda tilde T like this. Okay. So if you stare at it, there are three components. This one is the deterministic, meaning it does not affect the simulation or does not affect the randomness, right? The distribution of S big T. This is the Brownian motion component part, of course, right, which is normal. And this is the Poisson part, which is discrete. But this and this are independent. In other words, actually, there's no single name for this, right? This guy right here. But component-wise, they're very easy to understand. There is a numerical, right, constant component. There is a normal component, and there's a Poisson component. And you just piece them together using the exponential structure and multiply them. In other words, right, suppose you were to do something like this. Okay. Then what would it be, right? Let me see here. Yes. So basically, it will be, right, integrating out these two components right here in terms of the expectation. So you will have this, right? And you will have this. And one thing that I want to tell you ahead of time is that these things are just kind of really long to write down, right? The concept is not hard. Sorry. Yeah, okay. Maybe let me do Y. Okay. So first I integrate in terms of X. So this is time, okay? So you see what I'm doing here. First with this. Okay. And then after I do that, I will sum for Y from 0 to infinity of e to the minus lambda tilde t to the Y over Y factorial. Does that scare you yet? Do you understand what this means? Okay. Other students, are you okay with this? So this, right, I hope you see is just taking expectation with respect to the normal and with the Poisson. Yes, and that independent, that's why you can just first do the Brownian motion and then do the Poisson part, right? If they're not independent, then this calculation is questionable. All right. But this is what I mean by understanding what the distribution of ST is. By the way, right, if the gamma is equal to 0, meaning you don't have this part, right, and you don't have this part, then what does this become? If gamma equal to 0, right, you don't have these parts, then what does this become? You can. Good question, Meet. You can, right? But I will tell you why I want to do the integral first, because that's actually my question. If these parts are 0, right? You can switch, but why do you think I want to do the integral first? Because without a sum, right? Without a sum part, do you know what this is? Exactly. It's the Black-Scholes formula. It's the Black-Scholes formula. Okay. So therefore, right, with this part in, is this still a Black-Scholes formula, even ignoring this? So when gamma is not equal to 0, is this still a Black-Scholes formula? The answer is a little, right? But you have to modify your Black-Scholes. Not really, Cherry. Not really. But I can turn. Oh. I see what you mean. I see what you mean, Cherry. Yeah, I should be careful, right? You're right. You're right. I should turn it off on both sides. You're right. Yeah, good question. I mean, I forgot that, but sure. Sorry. You should. I should turn it off. turn it off there too. Basically, I mean, I want to cancel completely. You're right. I was a little bit careless there, right? But the point is this now, right? Even with the whole thing present like this, even with the gamma and the lambda tilde present, okay? What I claim, and is too technical, and it's not really the main point of the class, is you can still relate this to some kind of Black-Scholes formula, modified to include y, and let's say, like Sherry pointed out, lambda tilde. Is that okay? So what I'm pointing out here is it's like a Black-Scholes formula that somehow involves the y component, which is the Poisson component, and then you integrate out that component. And that's why, in terms of Mead's question, I want to do the integral first, because I want to highlight the Black-Scholes formula first. But I want to emphasize, right? It's not really your day-to-day Black-Scholes. You have to modify, right, to include this component and this component, which basically, right, just affect the drift, of the term. Is that okay? So you see why, right? There is no explicit formula for the call like Black-Scholes type. With so that's the question here, right? Any formula, right? The answer is yeah, there's some kind of formula like this. Okay, but this is actually the taste that we have to live with, all right? As you'll see down the road with exotic option, that we can get some formula, but the formula will not be as clean as Black-Scholes. And by the way, right, Black-Scholes, the first time anyone see Black-Scholes, they're like, that's a crazy formula. Well, guess what? Black-Scholes is as nice as it can have, right, compared to something like this. But still, my point being, right, is that if you are so focused on the level of the formula and symbols, you won't see through the whole thing here. The thinking, I hope like I'm trying to pass on to you, is a structural thinking, right? You block it out. Okay, here's the Black-Scholes component. I mean, here's the Brownian motion component. I see it as a Black-Scholes like type of thing. And then I see some integration that there's no standard thing to reduce it to, so I just keep it. But this Black-Scholes thing will allow me to simplify this calculation a little bit. I just have to work out the symbolic connection, right, between this and my regular Black-Scholes. Is that okay? Any question here? All right. So I'll leave it like this. All right, and move on to the next component, which is the PDE, right? Partial differential difference equation. Okay. So first of all, let me show you, right, the result, because again, like I said, writing this is tiresome, and let me just show you the result from the textbook or from the notes. So here's the notes, and right here. Oh, by the way, right, when Cherry was asking the question, This is this one that I was referring to, Ito's formula for jump processes. And it will come out to be something like this. I mean, actually, this is the generic form. We'll discuss this, okay? But what I want to point out to you is the nature of the equation, which is in chapter 3, right here, partial differential difference equation, only with Poisson noise. And the equation is like this. And by the way, right, let me say this. This equation does not include the Brownian motion component. So we'll put that in, all right? We'll put that in. But so look at this and see what you observe. C here is the V, okay, is the call option price. It's a function of time and the stock price, X, right? So imagine that there is another component right here, plus 1/2 sigma square, X square, second derivative. Then compare this with your good old Black-Scholes. Oh, sorry, the traditional Black-Scholes PD that you know. What do you observe? Anyone see anything similar or different to your traditional Black-Scholes PD? Do you memorize that PD? I think it's actually quite useful, right, to memorize a Black-Scholes PD. Why? It's not just a PD in the scary sense that you have to know PD. In finance language, it's a connection between the Greeks. All right, look at it from that point of view, right? I'm not big on PDs. All right, and so you guys go out in industry. Industry doesn't worry about PD too much, but they definitely care a lot for Greeks. And so you recognize that it's just two different languages to talk of the same thing. I'm sure traders out there, right, care about the relationship between the gamma, the delta, the theta. And guess what? Those are connected by the Black-Scholes PD, right? Or more or less, they should follow that rule. If that rule is violated, it tells you something about the behavior of the stock that does not conform to the Black-Scholes model, which is valuable information, okay? So anytime you come upon a PDE, think of it from the Greeks' point of view. Then you will bring the whole new financial angle to it. So right here, right, this is the one that I just showed you, but now it is enhanced with the Brownian motion component, which is what I intended. So this is the equation, right, for the jump component, and the differential refers to this, and this. The difference refers to this. Okay. So what is the traditional Black-Scholes fee? What is it? It will be this, right? So maybe let me do V sub t. Okay. So when you come upon a PD, I ask that you roughly know two things. Why this way? Meaning, why does it look like that structure? And how to compare that with the traditional one. As you can see, that's the kind of question I keep asking you in homework, in worksheet, in exam, the kind of thing. That's all you need to know, right? That's all you need to think about. Like, okay, I got a new thing. How do we get that? All right, what's the reason? Even you don't need to know the deep down technical reason, but structurally, what's going on? Okay. And second, all right, this is a new thing. How does it compare to my old thing? Why is it there? Right? Which one's better or which one's more appropriate? That kind of thing. All right. So maybe we look at the why later. Let's look at the compare, right? That's even more realistic. How do the two equations compare? What do they have that are the same, and what's the difference? And where does the difference come from? Oh, by the way, right? What the heck am I doing here? There's no lambda tilde, right? Yeah, no, thank you, Sherry. I never pay attention to that. Yeah. Okay, so I guess Sherry pointed out one thing, right? That there's none of this, which is clear, right? Where does this come from? Or rather, right? Sorry, this should be lambda tilde times gamma. Where does this come from? This comes from the jump component, right? That's clear. Also, where does this come from? Oh, and by the way, sorry, I copied without, right? Gamma. The sigma in the note is the gamma here for us. Where does it come from? This also comes from the jump component of the Poisson, right? Because each time the Poisson jumps, the stock price jump with a percentage of 1 plus gamma. Okay. So from the point of view of Greeks, what do we say? Well, you say that, right? In the traditional Black-Scholes world, the Greeks combine this way. In other words, the theta plus the delta plus the gamma, right, in this proportion is equal to R times the auction value. Is it the same here? Well, not quite, right? The gamma and the theta is still the same, right? This is still RV on the right-hand side. But the delta component got compensated, right? This is a compensation. But then, of course, you still have this part right here, which is the jump part, right? And by the way, let me ask you a very practical question. Let's say this is on interview, right? And the interviewer wants to see if you can read some math. He will ask, tell me, is this term positive, negative, or neither? Meaning sometimes positive, sometimes negative. What can you say? This term right here, is it positive, negative, or neither? Okay, let's think about it. What does this mean? What does this V of T something something means? What does it represent?
It represents like the V equation, but instead of X, it's in terms of like X times 1 plus
So what is V, Don? What does V represent here?
V is the equation for the stock price.
No, not stock price.
Oh, I'm sorry. Never mind.
What is the stock price here? What symbol is the stock price here?
Zero, but
Sorry? I should not call X, right? I should call it
I don't
S,
know.
right? So S is a stock price. What does V represent?
The call option price?
Correct. And how does,
Okay, I see.
what option we're looking at here? We're looking at the call option. Yeah, you said call option.
Yeah.
So how does
Mhm.
call option connect to the stock? What is the basic relation between call option and a stock without any model, right? Just think of market.
It's basically has like the stock. It calculates the maximum of the stock and the strike price.
No, yeah, but that's at the payoff.
But that's only for the European call, I think.
Yeah, European call. So here, right, what do you notice between these two terms? Which term is higher?
Definitely the first one, because like at the stock price is multiplied by 1 plus.
Right. But if the stock price is higher here, do you think the call option price is higher?
Yeah.
Right, because it's call option.
That's going to be greater.
Exactly. So this term is going to be just.
Yeah.
Okay. So that's how you think about it. Exactly. That you see, that just understanding what this term means, right? That tells you that this term right here is positive.
Okay.
That's it, always. Right. And so you see, it's not as scary as it looks, right? It's something you can reason out. And of course, right here it says that basically if the stock price jumps up, then the call option price also jumps up. But now let's go back to, right, our grand scheme of the relation between theta, delta, and gamma, right? You see that the scale, right, of the gamma and the theta is the same. This is the same. This gets compensated, but this gets added back, right, with another term. So if you were to guess, right, roughly speaking, how does the delta, gamma, and theta of the model with jump compare with the delta, gamma, and theta of the model without jumps? How do they compare? What do you think? Again, right, this is a very heuristic question, right? Interview question type maybe, just to ask you to gauge what you can see out of this equation. What do you think? I claim that from this equation, right, the relation are probably roughly the same, or the values probably are roughly similar to the ones without a jump model. I could be completely off, right? But the reason for my thinking is because, right, the scale here are the same, first of all. The scale here got reduced, yet it got put back. Of course, right, whatever this got put back here, and this are not related at all. So that's why I say I can be completely off, right? There could be some values that would just put me out of, my ballpark. But roughly speaking, I think because of compensation here with a minus, right, and then this is a plus, seems like they kind of make up for each other. So of course, right, these two models cannot be exactly the same, cannot be. But I would say that the difference is not too dramatic. All right. You understand what I'm trying to say? And if you want to test my guess, what would you do? If you were to test my guess, what would you do? Well, you would run some simulation.
Actually just like try it out.
Yeah, right. Like actually like your homework of this week. You try it out with two models, but you need to make sure that you're comparing apples with apples. In other words, you want to make sure that somehow, right, that the sigma, right, are comparable, that kind of thing.
Yeah.
Right.
What
And
just like see if they're similar since they're both equal to 0? If like they're the
So,
same.
this is not, so of course, right, comparing two models are always tricky because of
Yeah.
course the whole point of having a different model is you're talking about a different phenomenon, right?
Right.
But what we're saying, right, is not that they're both equal to 0, of course, because that's an equation. What we're saying is out of this equation, what do we get? And what financial quantities do we care about? Well, we care about the gamma, the delta, and the theta, right? And you can imagine at home that the model, right, when under the jump and without jump, the gamma are different, the delta are different, the theta are different. Yes. Now put yourself into a trader's point of view. If you as a quant comes tell him, look, boss, right? If I run the Black-Scholes model, I get this value of delta. If I run the model with jump, I got this value of delta. Then guess what your boss will tell you? Well, guess what the trader will tell you? They will tell you, right, that, well, tell me what model to use. Okay, you're the quant. All right. I mean, like, I'm here to, I hire you to tell me what the value of the delta is, not to tell me that you have so many models with so many different answers. Does that make sense? So picking the appropriate model to use is, of course, I guess your job, right, as a quant. But I guess what I'm trying to say here is, if you run across different models, at least you should hope that, right, they have some relation somehow, right? That the value of the delta here and the value of delta here, I think, are not completely different as long as you calibrate the parameters to similar levels. Does that make sense? And that's just a guess. But as a quant, you would probably feel comfortable to report to your boss that under these different models, you have different values, but they're not dramatically different. By the way, actually, that may not be super comfortable to begin with, because in the world of finance, right, a difference of 1% can mean a lot already. Okay, so even if this and this are different by 1%, who knows? That could be dramatic. But what I'm trying to say is, right, at a classroom level, at least we can try to gauge that how much different do these models compare, right? I'll give you another simple question, not too simple, but a question that should come to your mind. You did the exercise, right, to find the implied volatility under a Black-Scholes model. And by the way, that's all people do, right? For implied volatility, they use Black-Scholes model. But the concept of implied volatility is clearly applied to any other model, right? It applies to the model with jump too. Have you ever thought of, if you were to apply a model with jump, right, to this exercise, what kind of implied volatility will you get? Would that be similar to Yahoo Finance? Bigger, smaller? How different? And suppose it's different, can you claim that the model with jump is more appropriate, and why? Okay. Now, I'm proposing this question. I'm not trying to say that I know the answer to this question, right? You can try it out for sure. But giving intelligent answer to these kind of questions will be hard, right? Because again, it comes to model selection. But at least you should be able to see that you can try out these models onto real world data and draw some sensible conclusion out of it. That's all I ask you to do, right? Knowing which one to use, right, is probably a level that is even beyond me, right? So I definitely won't, ask you to go there. But right, comparing models, like what I'm asking you to do here, is the first step, right, to do so. Does it make sense?
Yes.
All right. Any question? So that reminds me, right, that what I wrote down here is wrong. I should need a gamma here, right? And yeah, I miss a gamma here. I miss a gamma here, right? The gamma comes from this gamma, right? So when I put this in here, I need the gamma. This part is fine because I was doing, wait, hold on. This part I need a gamma too because this is risk neutral. Okay. All right. So again, right, basic message, try to relate your new PD to the old PD. All right, that's the basic relation between the Greeks under different models. So now let's go to the why part, why this is true, right? Why the PD? So why the PD, right? Meaning how do you derive the PD? I guess that goes back to the original question. Why the Black-Scholes PD? Meaning, how did we derive the Black-Scholes PD? Based on what principle? Do you remember that? Because if you remember that principle, it's the same principle that allows us to do the new one. So it's this, right? Why the Black-Scholes PD is this, that it relies on the fact that if you have a martingale, okay, then DMT equals to alpha T dt plus sigma T some another martingale, right? Let's say, you know, oh my gosh, I'm running out of, okay, let me say X, all right, X. Well, MT is another martingale. So basically, if you decompose a martingale into another underlying martingale and a DT component, then this DT component must be zero. So a martingale cannot have drift. You know, simply put, a martingale cannot have drift. All right, it should have zero drift because this part right here already, right, captures the martingale component. If you add any kind of drift, you will spoil the martingale property. So in the classical Black-Scholes PDE, what do you have? In the classical Black-Scholes PDE, what you have is your martingale is e to the minus RT times VT, your call option price. And so when you apply EDOs, you will get minus RV, right? Minus R times e to the minus RT VT. Let me just do this, V VT, and then plus e to the minus RT partial TV, also VT, and then plus e to the minus RT partial stop, right? VEST plus e to the minus RT 1/2 second derivative V, right? That's the quadratic equal to 0. Okay, and then you collect all the DT component, right, in all these guys and set it equal to 0. And that basically gives you this. Okay. Any question? Right? Do you recall this? This is what we discussed a couple lectures ago. So the same principle applies here. Okay, except two things. That we need, right, need to pay attention to the martingale component generated by the Poisson process. That's new, right? Before, remember, right, this is just like we say, this is some drift and some martingale. In the Black-Scholes model, the martingale is only the Brownian motion part. Therefore, right, it will become sigma square s square dt, right? Sigma square s square dt, and that's why you just have this. But now you have the Brownian motion component and the Poisson component. And that's why, you know, here you have this component for the Brownian motion and this component for the Poisson. That's why, right? But second of all, you still need to pay attention to an Ito's formula for jump processes. And this is actually Sherry's question, right? Sherry was asking, I guess, when I was doing something like this, right? I suppressed, or I did not write down what this is, right? The reason is because, you know, this is applying Ito's formula, right? Even though it's a very easy level, but because there's a Poisson component, and I did not tell you what it is. That's why, right? I did not write it down. But we are applying Ito's formula at a more serious level here, because we will apply Ito's formula to the discounted option price, right? So we need to know the more you know, like the rigorous version of the Ito's formula. Any question? Okay, so let me write down the formulation, all right, of Ito's formula for jump processes. So the general formulation is like this. We have generally dxt, right, to be, or a process has a continuous component plus a jump component. Okay. For example, right, when we write dst to be, let's say, r st dt plus sigma st dw tilde t plus gamma st minus d nt minus lambda t, lambda tilde. Right? So clearly, for x here is a stock, all right? Or discounted stock, doesn't matter, but stock for now. What do I mean by the continuous component? And what do I mean by the jump component in this case? Can anyone tell me? What do I mean by the continuous component? And what do I mean by the pure jump component? What do you think?
So the continuous exponent is the factor of the equation that keeps on going, but like the jump is just like a constant.
Right. So here, which one is which dot? That's what I'm asking.
Gonna guess that our STDT is continuous.
Yes, that's correct. Anything else?
Is sigma ST also continuous?
Sure, because the Brown motion is
Yeah, because that's the Brownian motion under the P.
continuous, right?
Yeah,
So
and
this
like the rest of the equation is the pure jump factor.
not quite. It's a little
Oh.
tricky. Why? Do you see another continuous component?
Oh, yeah, that's right.
Which one?
The rest of the equation, which is like gamma ST minus. Yeah, that.
No, that's not. That's by itself is not nothing. So what's the
Oh wait, that's not continuous.
the last continuous component is this guy right here. Because actually also dt.
Okay.
Okay, we compensated. So that's why we put it next to the Poisson process. But its place might also be here. Does that make sense? So really, right, the continuous component is R minus lambda tilde times gamma STDT plus sigma STDW tilde T plus gamma ST minus DNT. So this is the continuous component, and this is the pure jump component. Are we okay? So I notice how we get closer and closer to this. Do you see that? Okay. But I haven't told you, right, how the Ito's formula works. So Ito's formula works in a very similar way as before. So now you have a function of t and xt, right? And you want to find df. You understand? Right? You want to find the differential. Well, except, right, that, okay, we can do that. So basically, first of all, it's the same thing. So will be partial with respect to t, partial with respect to x. But then if you do partial with respect to x, it's only the continuous component. And then the quadratic variation of the continuous component. And then the last part is a little bit peculiar. It's just f of t xt like that. Okay, so this is the jump component. And I want to say this, no general to J. There could be some particular ones. The relation depends on the problem. Okay. But do you understand at least roughly what this formula say? Can anyone, right, verbalize what this formula is telling us and why you think all the pieces make sense or not? I don't know. Maybe this formula just scares you, right, a lot, and you have no idea what's going on. Or if you think it makes rough sense, can you tell me, right, why each piece falls into place as they are?
For when we do the derivatives of the continuous components, is it to avoid the fact that like it might be 0 at the jumps?
Yeah, Cherry, or let's put it this way, right? What you say is correct except for the avoid part. We're not avoiding anything, right? What's the philosophy of handling things with jump? Right here, actually. Meaning we look at the place where there's no jump and we look at the place where there's jump. Now,
Okay.
when there's no jump, when there's no jump, how does the process F move? When there's no jump, that means this is turned off, right? The J part is turned off. Agree? When there's no jump in stock in the X, that means X behaves like the continuous part, right? Therefore, any movement of the function will depend only on the continuous part of X. But when there's a jump, okay, when there is jump, if X jumps, how much does the function jump? There actually you don't know, right? If X jumps, how much does the function jump? So you don't know. So all you can say is the new value minus the previous value. So this is when the function doesn't jump, and this is when the function jumps. That's it. That's really it.
I also have a really quick question. It might be minor, but when we separated this into like the continuous and jump components,
Yeah.
like that term, like gamma st minus d, and like that term over there,
Yeah.
how come we don't, sorry, the line above it,
Yeah.
like how come we don't care that it's st minus when um, we use like the gamma t part, like when we factor it?
No, that's a great question. So your question is formulated like this. St minus dt is equal to st dt, isn't it?
Yeah, exactly.
Right? And by the way, it's a great question, right? But I hope that since you have such a good question, you can push ahead to see what your answer should be. First of all, right, with your question, this is what you're asking. Now, can you propose to me a sensible way for you to test out this answer? This question.
I'm not sure. Like, am I supposed to solve it mathematically or with code? Can I get like a hint?
Solving is too quick of a word, right? A lot of mathematical object we do has meaning. You're not solving for anything unless you have an equation, right? So you want to put meaning into them. So here you're purely putting them at symbolic level, which is fine because right, it's fair for you to ask me that because right, here's st minus here. Why when I transfer it here, I suppress the minus, right? You notice that, which is very good. But symbolically is this, but meaning wise, right? What is it? Because without putting a meaning into these symbols, right, you're not going to cancel like this, right? A high school student will say, of course that's wrong, because if you cancel it, right, it doesn't work. But that's not the meaning, right? What's the meaning?
Like I tried to make sense of it as like the deltas, like
No,
no, okay.
I'm not sure I pushed this point too much in this class, but a differential only makes sense where, or where do you where does the differential really come back to life? This is just a symbol. When do they come back to life? Remember when I asked you to prove something like this, right? Or this. And this is where some of you, I criticize you on your homework submission because your approach actually does not carry the mathematical meaning of things. Remember what was the right methodology to test this out? You test them out in an integral.
Oh, right, and then we do the like a summation, like
Correct. because
Okay.
summation is the integral, right, in the limit. But
Oh, and
what? Go
sorry,
ahead.
is it because it's like a Riemann integral? It doesn't matter if it's the left or right limit?
Absolutely, that's exactly it.
Oh, okay, thank you. Yeah, thank you so much.
No, it's fine. But once you exactly understand the meaning of the procedure you're doing, something just connects. Yes. But when you kind of fumble around in the symbols, mysterious, whatever you're thinking, then of course, right, things just look mysterious, right? But I was just showing you that you're capable of thinking that way, as long as you put it in the right context. Is that okay? But you're right. It's ultimately because Riemann integral does not care if it's left, right, middle, whatever, right? And or if you want to wax some, kind of, more poetical way to put it, is because this is continuous, so it doesn't care. But yeah, that let's not deal with that, right? Let's just say that it's a Riemann integral. Yeah. All right. So that's a good question. All right. So where were we? Yes. So yeah. Any other question on this EOS formula? So I hope that that makes some intuitive sense. Okay. No question, right? So the next step you take when you learn math, by the way, right, is you understand things intuitively, like this, question how the pieces, right, fit together, like we just did so far. But the next simple thing you can do for yourself is to test out this, glorious formula that your professor told you in some simple example. Okay, try a simple example. To see if it works. Okay, if it doesn't work, that means that you understand it wrong, or the formula your professor told you is wrong, right? Which is probably it's not unheard of. So what do you propose that we test? How do we test out this formula on simple cases to see if things make sense? Anyone? So one thing you can always test for, right, is actually you should recognize this too. When something is proposed, you should recognize if it's an extension of the old thinking or it's completely new. Is this EOS formula completely new? I hope not, right? This is an extension of the old EOS formula, which, by the way, as I pointed out a long time ago, is an extension of your classical calculus, right? So EOS formula is an extension of classical calculus when you add the Brownian motion component. And now this one is the extension of the other EOS formula when you add the jump component. That's it. So one way for you to test if the extension makes sense is to turn off whatever component that caused the extension to see if your formula for the extension collapsed back to your old one. In other words, test for consistency, right? So here, for example, let's take this. How do I turn off the jump component? I can turn off the jump component by making gamma equal to 0, right? And by the way, Cherry, right? Actually, now things are good, because if I turn off the gamma here, I also turn off the gamma here. So what was wrong before was because I forgot the gamma also goes with lambda theorem, right?
Okay, yeah, thank you.
No, it's fine. No, it's cool. It's good that you pointed out, but yeah, it turns out to be consistent. I just need to turn off gamma here, but okay. But if I turn off the gamma here, right, then it goes back to the good old Black-Scholes model, right, where this is the component. Now look at the new EOS formula. This is in the old one. This is in the old one because the component, right, is just this. This is in the old one. What about this? Because I turn off the gamma, this doesn't jump anymore, right? Therefore, this one get completely turned off. In other words, at least, right, it passed a simple test of consistency. That if there's no jump in this, then there's no jump in this, and it just goes back to the old Black-Scholes model, the old Edos formula. Are we okay? All right. 2. Now, what's another easy one? Let's not have any. Let's not have any continuous part. Let's just try it out on pure jump. What is the pure jump only process that we know? Well, we know this, right? Let's say we look at this. dst is gamma st minus dnt. This is pure jump only. What is the formula for st here? What is the explicit formula for st here? St is S0 1 plus gamma times nt, right? Now, if our Edos formula is any good, it should allow us to recover the st from here. Do you agree? Right? We should be able to recover dst from here with our Edos formula. But guess what our Edos formula says? It says that dst is, well, this is off, this is off, this is off, because st is pure jump only. So it has only this. Well, so it does not tell us much. It just says this, right? Right here. Are we okay? But is this? Are you kidding me, right? What's going on here? Edos formula doesn't work, right? How come that? So you understand, right? I want to go from B to A, right? But Edos formula doesn't tell me that, does it? Well, it does. All right, it does. How? Because you're not applying B yet, right? Doing this, you only just apply Edos formula. You did not look into B yet. Well, what does B tell you about the relation between st and st minus? Well, if anything, right? If st is this, right? If st is this, then st minus should be this with a minus. Do you agree? So in other words, if you plug in you get this. Do you agree?
Yeah, I could see that.
How do you resolve this then? How do you resolve this? you resolve this by somehow link a connection between NT and NT minus. Now, please tell me what is the connection between NT and NT minus?
It's if n is like a counting process, then like NT minus would be like 1 or something.
Correct, right? But you just have to be careful, let's say at jump points, right?
Right,
At
right.
jump points, because otherwise, right, if no jump, then NT equals NT minus, right? But of course, clearly here, what we care for is at jump points, right? So actually, you should do both, right? But anyway, so at jump points, NT is equal to NT minus plus 1. Or, let me do this, okay? Let me do this. This is always correct. And this may look like a trick, but NT is NT minus plus delta NT. This is always true, right? It's a truism because that's that definition, right, of what delta NT is. But of course, you can say something a little more meaningful, like delta NT is 0 if no jump, right? Delta NT equals to 1 at jump, something like that, right? But
Yeah, that's
of course,
generally the definition.
yeah, of course, this is the DNT that we're referring to, right? So let's see. So here, then we can resolve it into or I can even be bold and say DNT, right? It's the same thing. So maybe let me change that to DNT to make it everything consistent. Are we okay? Okay. All right, so let's resolve it one last time. What is this? This is?
Is that ST minus?
Yeah. What about this? Do we observe anything interesting here? Well, let's think about it. How many cases can DNT be? 2 cases, right? Either 1 or 0. If DNT is 0, what is this?
And that's just 0.
Correct. If DNT is 1, what is this?
That's gamma.
Right. And do you agree then I can write like this?
Yes.
Right? Because if it's 0, then it's 0. If it's 1, it's gamma, which is perfectly matching what we're looking at. So you see, but which is exactly A. So we're done. But you see, the beautiful resolution of this to this is because DNT is 0 or 1. If DNT is something else, then the resolution won't be this to begin with, right? But of course, maybe the abstract formula is not that to begin with. But all in all, right, the Ito's formula is consistent because we can recover A from B. Are you okay here? Are we okay here? You understand the whole logic?
Yeah, it makes a lot of sense.
Yeah. All right. Thank you, Don. So now let's try a complex case, which is right the case that we're looking at. For example, the ST is RST dt plus gamma ST, sorry, not gamma yet, right? Sigma ST dW tilde T plus gamma ST minus, right? D and T minus lambda tilde T. Okay. We claim, right, before we wave 10, and say, yeah, you know what? It's going to be e to the, sorry, right? S0 e to the r minus, right? 1/2 sigma square minus gamma lambda tilde t sigma w tilde t and t, right? I don't know where I want to put it. I probably want to put it here. 1 plus gamma raised to nt, right? Like that. All right. Sorry, not dst, right? St. Fine. So let's remind you of the big Ito's formula, right? So df txt is, right, what is it? F sub t dt, f sub x dx continuous plus 1/2 f sub xx continuous quadratic, and then plus a jump. Okay. So again, right, our goal is to recover A from B, right? In other words, we want to test out this Ito's formula on this case. All right. So actually, you know what? In that sense, then maybe I should write like this, right? So tell me, first of all, right, when you do something like this, you better know what your continuous component is, and then what a pure jump component is, right, in this language. So in this structure, right, can you tell me, by the way, what's your function, right? What is your function? What's your continuous component? What's your jump component? Does it make sense? Because if you want to apply it, you better know where the components are. Can anyone tell me?
The jump components are anything with a gamma, I'm assuming.
You gotta be careful there, like, right, Sherry, because there's a gamma here too. Do you mean this is a jump component too?
Oh, is it not? Sorry.
No, right? And I think as Dawn pointed out, and actually Dawn missed at the beginning, right? This belongs to the continuous component because it's dt.
Oh, okay.
So, right?
Like the nt is part of like the jump
Anything
component.
that there's an association with n, not gamma, right? Gamma is just the inflation factor. Gamma is the parameter. It doesn't make you jump or not jump, right?
Oh, I see. Okay.
Anything associated with n. So in here, right, which part is associated with n?
Just the last term then.
Correct. So the jump component is nt log of 1 plus gamma, right? What's our continuous component? Well, our continuous component you can think of is just this part, because you kind of put the t in here. It's up to you, you know. You could put the you could put you could say that this is a whole x. You can think of this as a whole x, actually, right? So maybe you can do that. So actually, this is only f of x, which is S0 e to the x, where xt is r minus 1/2 sigma square minus gamma lambda tilde t And this is your continuous component. Does that make sense? Okay. So let's try the EDOS formula. And actually you see it's almost straightforward, right? Because what is then df, right? Meaning, so of course, right, f of x here represent the stock, right? So dst will be what? There's no t component because we include the t component in the x, so that's fine. So first of all, right, going to be the partial with respect to x. But of course, the partial with respect to x recover the stock. So it's going to be just st, right? D continuous component. And then the second derivative. But again, the second derivative also recovers the stock. So plus 1/2 d, and then plus the jump, whatever that is. Are we okay? So do you see, right, that this would this be my function, right? Differentiating with respect to x recover the stock. Differentiating stock twice also recover the stock. Yes, that's it. The rest are just writing down EDOS form. Now finally, right? Not finally, I need to resolve what this and this are. Well, you see that this is right here already, right? And this should be sigma square dt because of this, right? So you see that if I plug this in, I already recover this part right here and this part right here. If I plug in, or maybe, right, let me not skip things and let me just replace it for you. Right, this is the first component. Second component. Okay, what's the third component? What is the jump of the ST? What is the jump of ST? So here's the thing, right? The jump of ST, notice it comes from here, which actually is here, like that. Now, do you see that our analysis here, is it any different if we include this component? You understand what I'm trying to say? If we were to recalculate, right? Of course, what will be different is instead of S0, you have to include this whole thing in for S0. But after all the analysis, the final answer, is it any different? You understand what I'm trying to say, right? This part plugs in here into S0 because, right, that's ST now. But, right, this part doesn't play any role because here we're analyzing the jump. The jump action is exactly the same as before. Therefore, ST minus ST minus is the same as before. In other words, it's still this. Are you okay? And now, right, this cancel with this, giving you RSTDT, right, plus sigma STDW tilde T plus gamma ST minus DNT minus lambda tilde T as desired. Any question?
Wait, sorry.
Yeah,
Would it be okay if you like briefly explain the like thought process? Maybe not the individual steps, but like the thought process.
of Ito's formula?
Yeah, because like even the FX step kind of like I can follow it, but I don't really understand why we decided to represent it like that way.
Okay, so you mean like, why do I represent the function like this, right?
Yeah, like I understand like that it works, but I just don't understand like how to come up with that thinking right off the bat.
Yeah, no, that's fine, right? This is the structure, isn't it? That's whatever we want to call F, right? So the question is to decide what is X. Okay, what is big X? Well, we already decided this is our jump component, right? This is our jump component. So we need to decide what the continuous component is. And here actually you have two choices. You can just call this the continuous component. And then this will be the T part that Ft depends on. Okay. So in that sense, then your f of tx, if you want to call that, then f of tx will be e to the r minus 1/2 sigma square minus lambda gamma tilde t plus x, where now my x does not have this component. It only has this. Or I can transfer this part into x and just simplify my f to this. So before, right, I would have to have f of tx. Now I only have f of x. But the result is, of course, the same. Why? Because in one case, I differentiate with respect to t and do a dt. In another case, the dxt takes care of it for me. I hope that makes sense. Does it or no? Is that the question, or even a little more complicated than that? I can do an example to show you.
That makes sense. I was just wondering what like triggers that mindset, but then that makes sense because you said you can do it two ways, but this probably makes it more simpler.
Yeah, you can do it two ways, but I mean, basically at the heart of it, right? This scary guy like here, right here, is just an exponential structure. All right, it's just an exponential structure. It's just an exponential structure of something. So our job, right? Actually, our mind of thinking actually is just isolate the Brownian motion component and the jump component and the t component, and that's roughly it. However you want to distribute these guys are really a matter of formality. And you see, that's exactly what we do here, right? This is the action of the Brownian motion component. Because in the quadratic variation, right, everything else disappears. Only the Brownian motion component survives. And then you have the jump component. So it's a very, very kind of separate thinking, and then you put the pieces together. You look at the dt component, you look at the dw component, and you look at the jump component, and you piece them together. That's the best I can put it, right? Formally, all these things I wrote down, but in mind, that's just that. Does that help, or any specific piece that is still confusing? Do point out, and I'll try to explain.
Right, yes, that helped. Thank you.
Sure. Again, right, I do acknowledge it's a bunch of symbols. And unfortunately, that's just what it is. But the idea actually are quite simple because you only are handling 3 components at most, okay? But because so many symbols running around, it may seem scary to keep track of things. But do not keep track of the symbols, keep track of the components, keep track of the ideas. Where's my T? Where's my brown motion? Where's my jump? That's really it. All right. So finally, let's go back to the original discounted version. So in other words, I have this. And I was wondering what the discounted, right, version is, right? That was my question. Okay, so tell me, right, what's the continuous version? Sorry, what's the continuous component? What's the jump component? And what's my function? What's my continuous version? What's my continuous component? Right here. What's my jump component? Right here. What's my f of tx? Well, this is what I'm proposing to solve, right? So f of tx is e to the minus rt times x. Okay. So what is d of this? So differentiate in t, right? So you see it's going to be minus r, oops, times this, right? And then what? Then differentiate in x. So that gives you e to the minus rt, right? And then d, the continuous component. So let's do sc, right? That's easier. Is there any second derivative component? No, because the second derivative is 0. And then plus the jump component, right? Plus f. Basically, let's do this for now. Do you agree? This is applying Ito's formula. Do you agree? But what is this, right? It will be minus r e to the minus rt s t dt plus e to the minus rt. This is the continuous component, right? So it will be rather r e to the minus rt st dt plus sigma e to the minus rt st dw tilde t, right? That's the continuous component. Okay, what about the jump? When I multiply e to the minus rt like this, because e to the minus rt does not jump, right? E to the minus rt is continuous. It will be st minus st minus. Sorry, right? Yeah, no, it's fine. Yeah, exactly this, right? But what is ST minus ST minus? Well, that's this. Oh, sorry, right? That's this. Ooh, so I make a mistake, right? The SC is, I made a mistake that I was pointing out to Don. I have this, right? So actually, I need what? I need R minus, right? Sorry. I need R minus lambda tilde gamma times this, right? Because that's a continuous component. I need to include this in. And then finally, right, this component comes out to be gamma ST minus DNT. And that's my final answer. Now I can turn this guy back into here if I want. So all in all, right, it goes back to what we say, that discounted stock price is differential, just end up subtracting a R into a drift. Subtracting the R into a drift. Everything else is the same. So you see this R and this R cancel. So indeed, right, if you want, it becomes something like this. E to minus RT, right, ST sigma EW tilde T plus E to minus RT gamma ST minus DNT minus lambda tilde T. And that's why it's a martingale, because the drift component completely cancel out. And this goes into the Poisson process for compensation. But again, right, this calculation is just demonstrating again the Ito's formula applied to jump process. Question? Okay, so I think it's a good spot to take a break. Let's take a 7 minutes break. So let's come back at 10:50. Okay, 10:50 my time. All right, I'll see you then. Okay, so I'm back. So let's continue. Any questions before we continue to the Black-Scholes PD for the jump, explaining how it's true? All right, so let me recap, all right, and I guess it comes with practice. I'll give you a few problems to work on, right, for the homework for you to see, right, the flavor of the Black-Scholes. But so, sorry, not Black-Scholes, Ito's. Ito was jump is Ito without jump plus jump analysis. Okay, and so that's at the risk of making it sounds really cheap, but it's really that Ito without jump, meaning just good old continuous version stuff. But the jump analysis right here is usually the tricky part. What can you say? Can you say something nice about it? Okay, like what we went through to get from here to here. That's what I mean by jump analysis. Okay. But anyway, right, let's apply this to get our Black-Scholes PD. What can we do, right? What we can do is this, right? So we know, right? We know that eta minus RT VT is a martingale. Discounted auction price is a martingale because of our pricing equation, right? Because in case anyone question you, you should know that it's because of this. Because but basically by definition, it's a martingale. So it's a martingale, so you can apply Ito's formula to it. Keep in mind that right now it's a function of the jump, right, of a process with jump. So now apply, right, Ito's formula to, right, V of TST, where ST now has a jump component, right? Exactly the same jump component we have in mind up here. Okay, so after we apply this, we just have to isolate whichever part that is dt and set equal to 0. But as you see, right, it will be a little bit trickier. But let's see, right? So d, right, eta minus RT. Oh, sorry. You need to discount it, right? Yeah. All right. So let me just do v, all right, to make it easy, where I don't need to write down the dependence. It'll be first differentiate with respect to t, so minus r v, right? Sorry, minus r eta minus rt v dt. That's easy. Second, right? Differentiate v with respect to t dt, because v depends on t. Okay. Third, differentiate v with respect to stock or x. But now we need to deal with the continuous component. Fourth, second derivative with the stock component. But now we need to do the quadratic variation. And finally, we need the jump component. Are we okay? Are we okay? So that's Ito's formula. Now I trust that we know what these are, right? We know what these are. Exactly the same as above, right? So the continuous component will be this part plus this part The quadratic variation is just this and this square, dt, right? The jump component is right here. So that's what we need to analyze. So right here, right? What is this? Okay. And what's our goal? Let's keep in mind our goal. Our goal is somehow turn it into a martingale driven component. All right. Because otherwise, right, the whole philosophy is, you remember, the whole principle once upon a time, what did we say it? Right? That you need to somehow look at the process as something driven by a martingale plus some dt component. Then you can conclude that dt component is 0. So the EOS formula does not give you the martingale-driven component exactly yet, because the continuous part, yes, right, it has the right motion. This is just dt. But this right here, right, does not have the dnt jumping out at you. Okay, this right here does not have the dnt jumping out at you. So we need to do that. That's what I mean by a martingale-driven component. Okay, so what is it? Well, first of all, the routine change is this. Is that okay? Relating st to st minus by a factor of 1 plus gamma, where it jumps. Second, leveraging the fact that dnt is 1 or 0. So this just equal to magically. Actually, it's not magic, right? It's the same because why? If this has no jump, right? If there's no jump. So actually, I mean, I should say this, right? I should say this rather. I should say that this is equal to this without the second, without this, because of course this is only true, right? If there's a jump. If not, then they're equal. So maybe let me just straight out write this. Like I won't have the middle part. Is that okay? The reason is, right, when st does not jump, then dnt is equal to 0. Then this whole term is 0. When st has a jump, then exactly the size of the jump is this. So therefore, right, this is equal to this. Before, when I wrote that, that's only when things jump. Right? If I don't have this, then that just capture only when jumps. It doesn't capture when not jump. So this in general captures that. So, but it's not a martingale-driven component yet. Why? Because my dnt is not a martingale. So I need to compensate. Okay. But of course, if I compensate, I need to add back. Okay. Because I mean, right, I only have this. So if I compensate, I need to return it. So all in all, what am I saying? I'm saying that the differential, right, of my discounted option price we'll have the following components: minus RV, V sub t, V sub x, the continuous component, V sub xx sigma square x square, right? And then this component. But right, so all right. So one more time, all right. The thing here is just we just need to keep track of the symbol. And then, right, so this, right, the continuous component will be R minus gamma lambda tilde, okay, st dt, and then plus sigma st dw tilde t. But this is the martingale, right? This is the martingale component, so I don't need to keep it here. I'll keep it in the martingale part, okay? And then plus, right here, 1/2, right, sigma square s square vxx, and then this part. Sorry. So the point is here, right? I just want to list out to you all the dt component. These are all dt component. And then you can confidently say that the other part is plus martingale. There are two martingale components. The compensated Poisson up here, that goes in here, and the Brownian motion that I erased, right? When I wrote the Brownian motion here, I erased, that goes into here. But the point being is, right, because this is a martingale, besides the martingale components, everything else must be 0. Everything else must be 0. But do you see that that's exactly the PD that we wrote a while ago? Right here. That's the PD. And you see the difference component, right, of the difference equation comes from exactly analyzing the jump part. And that's it. Any question? Okay. So now we're almost done, right, with this chapter. Let me say a few words on extension. Extension of the jump model. So one thing that may be, right, undesirable here is that the jump, right, is always positive. And jump size fixed. Okay, because the Poisson process, right, always jump up and jump up by 1, which translates to, right, this is always 1 plus gamma. Okay, how do we modify that, right? We can extend this by allowing for a random jump size. Okay, and this is captured by the notion of compound Poisson process. Okay, so what is compound Poisson process? Definition: a process Q of t is a compound Poisson process if it has the following representation. Not infinity. What do I want to call here? Let me call them yi, where yi are some IID random variables. Okay, and NT, of course, is a Poisson. Lambda process. And where the yi's and the NT are independent. All right. So what do we mean by this, right? What do we mean by this? So remember, right? NT is like a counting process. It counts up by 1. So basically, QT here is a random sum of the yi. Random in two senses. The number of summands, the number of terms is random. The number of terms is controlled by the n, and the terms themselves are controlled by the y, right? So actually, you see before, nt itself, right? This is a fancy way to write nt. Do you see that? If you sum up nt, right, with 1, then of course you recover nt. But here, right, instead of recovering NT, you change this to a random part. So in other words, the interpretation is this, right? In terms of picture, this is T, right? This is your NT. So suppose you start at 0, you go to 1, you go to 2, you go to 3, etc. Right, this is NT. What does your Q do? So this is tau 1, tau 2, tau 3, right? Your Q, so it starts out at 0 as well. Why? Because, you know, up to whatever value it is, NT is 0, right? Up to tau 1, NT is 0. So sum from 0 to 0 is 0, right? Nothing to sum. But of course, when NT starts to be 1, then you pick up one sides. So what does it do here? At this stage, at tau 1, while NT jumps up by 1, the QT will ask, okay, what's the value of y1? Maybe y1, you know, if you really want something crazy, you can say, like, let's say yi is normal 0, 1. It just jumped by a standard norm. Then, you know, then maybe the first value of y1 is negative, so it jumped down. Then like this at tau 2, right? So QT jumps exactly where NT jumps. But but the first size is y1. The second size, let's say, is still negative. Then that's y2. The third may be positive. Oh no, I should match things, right? Tau 3 is there. So the third is positive. Maybe it jumps up a little bit. So this is y3. So this is tau 3. Is that okay? So to get a compound Poisson, basically you just let the Poisson process run in the background. It tells you where the jump is. But then at the jump point, you do not use the jump size of the Poisson. You input some other random shock size of your choice. In that way, you'll get the model to be more general than just a positive jump. Any question? What does our stock model look like in this scenario? Our stock model will be DST is, let's say this, right? In the risk neutral version. There's a question. Yes, meet. And by the way, right? And I will say this, there's a beautiful result that says that what you're thinking of and what I'm describing are similar. But when you have two jump processes, in some way you can only capture two possible jumps, right? Because up and down. But here, I can have any kind of jumps I want, including continuous jump. With your two jump process, guarantee you will never be able to capture what I do. Because, right, basically I have any kind of jump size I want. Yes, but I'll explain, right, the connection between what you think and what I'm describing. But this definitely is more general than what you think. Yeah. So stock model, right, under risk neutral version would be RSTDT plus sigma STDW tilde T plus gamma ST minus DQT minus M tilde T. All right, what is this M tilde? This M tilde is the compensation. This M tilde is the compensation to make this into a martingale, right? Because you see, just because, right, your compound Poisson allows for jump up and down doesn't mean, for example, that it's going to be a martingale by itself. So M tilde is a compensation factor, which actually has a very easy calculation. It's expectation of the value of Q at 1. Expectation of Q at 1, okay? Which even has an easier calculation. It'll be lambda tilde times expectation of Y. So it's a product of two things. A, the rate of the Poisson process. Here is lambda tilde because we're in the risk neutral version. And the average of your jump size. So for example, if your jump size on average has size 0, like this, then automatically it's a martingale. You don't need to compensate anything. Okay. Now, there comes a lot of questions with this model, which we'll skip. How do we define, right, the change of measure kernel? What does the partial differential differential equation look like? Okay. Pricing via expectation. All very interesting questions. I will not say anything about any of this. See notes if you're interested. Okay, see the class notes. They're a little bit, they are very interesting, but they take us like into some territory that, a little bit, we don't have time for that. So you are responsible for the pure jump model, all right, on the exam, because I explained it. But if you are curious on how this extends to the compound Poisson and how the theory we just described extends to this, C class note, okay? They're interesting by themselves. I just want to tell you two things. First of all, it's a simulation, okay? I will ask you to simulate compound Poisson on your homework and possibly on exam with, pseudocodes, because I think simulation is easy, right? And it's exciting, it's interesting. So how to come up with the plots for compound Poisson, for example, would be something cool, right? Like I give you the code for the Poisson process, which jumps only one. Can you modify that code to allow for random jump size? All right, something like that. And then once you have that, then you can plug into the Monte Carlo simulation machine to get the pricing, right, going on. So that, right? So simulation you can do by yourself, or in the review session. Okay. So play around with compound Poisson, get a feel on how it works. But the second thing I want to tell you is a mathematical result that actually is connected to what Meet was asking or mentioning. Is this? There's a special case when the yi are discrete and finite. What do I mean by this? What I mean is the yi, right? Remember, yi is a random, right, jump size. And the compound Poisson does not put any restriction on what you can pick for the y. You can pick them to be normal, chi-square, gamma, let your imagination run wild. The only requirement it asks is IID. So in other words, right, the distribution of your jump are the same. You may claim that's a restriction. I want, at different points, my jump has different distributions. So sometimes it jump like normal, sometimes it jump like, I don't know, chi-square, whatever. That's doable, but that's like, a little bit like, that's just probably like putting two compound Poisson together, like what Meet was mentioning. So, but the IID, right, restriction is not that restrictive, right, because it does capture random jump size to begin with. But here, I want a very special type of jumps, discrete and finite. What it means is that the yi will take on values, right? y1, y2, up to let's say yn, okay? With probability p1, p2, up to pn, right? A special case is, for example, yi takes on value -1 and 1. Probably, again, right, what Meet would have in mind, with probability 1 minus p and p. P for going up, 1 minus p for going down, right? So in that sense, right, your compound Poisson will still be this. But because the yi's are discrete, okay, think about it. Because the yi is discrete, it's kind of interesting. Let's take this case. It's -1 and 1, right? So basically, if it's -1 and 1, if you track your compound Poisson, what you see is, right, sometimes it jumps up by 1, and then sometimes it jumps down by 1. Okay, like that. That's it. So what you could do is to collect all the positive jumps, all the positive jumps together and collect them into one process. You collect all the negative jumps and you put them into another process. In other words, you can break a compound Poisson here into a sum of So maybe let me do K here to make it not confused with N. Okay, so if I have K different jump sizes, then I can represent my compound Poisson as a sum of K different simple Poisson processes with jump size yi. What are the rates of these guys? Okay. So you understand what I'm trying to say? What I'm trying to say is, if I have, for example, a process, right, a compound Poisson process with random jump size of 1 to -1, I can alternatively think of them as a Poisson process which carry only positive jumps, and another Poisson process with a subtraction sign in front of it that carries only a negative jumps. These two have different rates. The rates are controlled by how often I want the positive jump to happen and how often I want the negative jump to happen. So exactly because of this result, what Mead was describing and what I'm describing are similar. Any question? We're okay? All right. So we're done with jump processes, all right? So in terms of notes, we're done with chapter 1 to 3. I mean, we're done because we skip over a lot of things, right? Namely the compound Poisson, etc. But it's okay, right? Read them if you're interested. So now we'll go to chapter 4, which, you know, even 5, 6, things like that. It deals with exotic options. Okay. So path-dependent options. We'll pay attention to 3 things. The barrier option, look back, and Asian, right? So the barrier option, right? I hope you have heard of these terms before. Basically gives either a up barrier or down barrier. And so basically your stock moves, right? And it could be, you know, strike out or strike in. For example, if this is strike out, then your option is worthless here if the expiration is big T. So this is called up and out, meaning if you're up above the barrier, then your option is worthless, right? But of course, there's also up and in, meaning if you are above the barrier, then your option starts to, you know, be you can get payoff, right? You may get payoff. But if you are never up in an up and in situation, then your option is worthless, right? Expires worthless. Look back says what it says. Basically, it's somehow to do with the max, right? Instead of getting, you know, a single value at time big T for your payment, you get the max of the stream, right? The Asian deals with the average. And so, you know, the barrier has its own taste, but you can actually kind of view the barrier as involving the max process somehow. Because right here, the barrier, right? The barrier is violated for the up and in if the max, right, is above the barrier. the barrier is never violated if the max is below the barrier. So it's kind of connected in some way, and you'll see. But the look back, right, and the Asian has the taste at least of, right. So by the way, right, look back doesn't have to be vanilla, meaning no strike. You can have look back call, right? In other words, you can have this. And you can have Asian call, right? So in other words, you see, I hope you see what's in the mind of someone who wants to buy this kind of option. So instead of like, you know, just dealing with this, right, which is vanilla call, what the customer wants, right, in the Asian case is they want the average behavior of the market, right, during the period investment versus a strike, rather than just counting on, right, the action on the last day. They want the average effect. Here, right, I guess this customer is very, I don't know, risk averse maybe. They don't just want the average effect, right? They want the best possible action, right, during the whole possible internal investment. Anyway, right, that's from the finance flavor. In terms of, right, mathematics, or in terms of quantitative techniques, our responsibility, of course, is to price these objects, okay, to price them. And by the way, right, there's nothing complicated about the model. We will use the Black-Scholes model, okay? No jump, no nothing, just Black-Scholes model. But you see that, right, even with the Black-Scholes model, these guys are not a walk in the park. The reason is because you are dealing with the whole path. So the randomness, right, just stacked up like that, right? Before you deal with a single random variable, right? Remember, I talked about the simulation. You deal with a single random variable. So you can have Black-Scholes formula, those kind of things. Now you deal with the whole path, right? Do you have any hope to get down to some formula and some PD, right? So Black-Scholes model. So question, right? Pricing formula and PD. And by the way, right, by PD, again, I do not mean any academic pedantic taste of PD. You can do that too, right? Professor Wu Jun may have a lot to tell you about how to do numerical solutions for PD. But from my point of view, right, very practical, the PD tells you how the Greeks are related. So, right, I mean, well, again, a friend of mine, alumni of our program, right, is a trader right now. He keeps telling me how he has to watch for his exotic option trader. He keeps telling me how he has to watch out for the gamma of his portfolio, right? He talks about how, I think he has something to do with a barrier option. He tells me how when the underlying is close to the barrier, the gamma moves a lot. I listen to it, roughly understand what he's saying, but not completely. So the point being is that, right, I mean, the Greeks, right, of the exotic options are super important, right, to the trader of those kind of options. So in other words, right, the PE itself plays some role, right, on making those decisions. So pricing formula, on the other hand, right, is a similar question in the sense that, okay, right, the PD tells me the relation between these guys, these Greeks. Can I get my hands on the numerical value of them, right? Your boss will want, okay, you know, I have a look back option, go ahead and please tell me what the delta of this look back call is, right? And you have had a little bit of a taste of that with the Asian option. And when you try to compute the delta with, simulation, go back to, I think, a couple review sessions ago, right? But the point being, I hope you see in that session is the calculation is very crude. The conversion is slow. Okay, two reasons, right? The first reason is we did not use any sophisticated simulation techniques. So if you want, right, I mean, Professor Larson, right, in his computational finance class will tell you faster ways to do that simulation, right? I'm not teaching you that. But another thing is, right, if you have a formula somehow, then you just plug in the formula. That will make it much, much faster than having to compute out the price by simulation, and then compute the Greeks out of those simulated price. You understand? So pricing formula is still completely valuable in these kind of scenarios, except that the pricing formula becomes super, super complicated. All right, and that's I'll show you. But complicated in the human mind, meaning there are many layers of formulas, but very nice in terms of computation because it just packages it into one single formula, right? Computationally, it's 5 seconds versus like 5 minutes if you have to simulate like a million scenarios to get down to your price. Does it make sense? So it boils down to us discussing the same kind of questions again, but I want you to see the practical aspects of why we discuss what we discuss. Any question? Okay. The barrier option is fine, right? I hope everyone has heard of or has seen the barrier option. Do I need to explain that more? You're okay, right? I hope you have seen that. Okay. So we don't have like much time left, so I would rather not start a new discussion. But let me tell you the important concepts coming up. So the first concept to cover is the notion of stopping time, which I suspect that Professor Larson did touch on, right, in Math Finance 1. But stopping time will come back to us for 2 reasons. In the barrier option, right, the first time that the barrier got hit, either in or out, doesn't matter, is an important time for us. Because the first time the barrier got hit, right, for the out option means up to that point, the option has some value. After that point, the option has no value because it's already expired, right, out of the barrier. But that time you see is a random time. It's not a fixed time in the whole trajectory, right? You run it again, it will be a different time. So, but it has a special property, right? I mean, it's a stopping time, meaning you will know when it happens by observing the trajectory of the stock. So we need to kind of, restate it if you forgot about it, right? And incorporate that in for the barrier option kind of discussion. Of course, stopping time will also show up when we discuss American option. So that's 2 places where the concept is important. Okay. In terms of pricing formula, right? In terms of pricing formula, like I mentioned, the look back and the barrier option both implicitly depends on something like a running max. Of the prime motion. In other words, it's going to be something like this. I think we call W hat. Maybe I'm wrong, but it's going to be the max of WT. Sorry, of W up to time T. Does it make sense? In other words, right, at any time T, you look at the history of W up to that time, see what the maximum value is. And that's going to be the value of this new process. It's running because this T, right, of course, keeps moving. So your max, right, keeps moving. I hope an easy observation here, right, to test if you understand what's been written down is W hat T is increasing in T. That's very easy, I hope. Do you see this? That W hat is an increasing process, meaning it cannot go down. It can only go up. Yes? No? Even though prime motion, right, can be up or down, whatever, crazy. This guy, its path is not that nice either, but it can only go up. You see that?
Yeah.
I mean, it can also be horizontal. Yes, Sherry?
Oh, sorry. I just said I was clear.
Yeah, right. Because basically, the more time you have, right, the more max you can have. You cannot go down. Yeah. Okay. But of course, I'm not just introducing this to make that, simple statement. We introduced this to handle the max of the stock. So in other words, to understand the max of the stock, we need to understand this. So we need to understand the distribution of the law. Okay, and that's to get to the pricing formula, and that's to do with the reflection, reflected Brownian motion or something. Okay, just reflection, and it's fine. We'll discuss that. Basically, by the technique of reflection, we will get our hands on the distribution of the running max. So this and this are big concepts. And then, plus some technical details, we kind of put them together to get to the pricing formula and the PD, right, for this exotic option. And that's the topic of next chapter, few chapters, 4, 5, or 6. So next couple lectures. Okay, that's what we have coming up. Any question? Next week is spring break, right? So we will return in 2 weeks. Yes. So that's where we're at.
Will there be any homeworks to work on during the break?
Yeah, there'll be double homework, right? Because you have another week off. So.
Oh, double the homework.
No, it'll be a usual homework, I guess. Yeah. All right, so I think it's a good place to stop here. If you have any questions on homework, whatever, I'll answer. If not, then
Hello, I would like to ask the problem 3 in your homework.
Yeah, what is problem 3? I forgot already.
Let J be a counting process. That is, J0 equals to 0. J has finitely many jumps on any finite intervals, and delta JT equals to 1 at any jump of point J.
I remember that. Yeah. So what's your question?
How to prove it?
Okay.
Part 1 for problem 3?
Yes.
Oh yeah. I think if you just like rewrite the integral in terms of like a sum where it's like JU and then triangle JU, you should be able to get to like those equations.
Yeah, I think part 1, what Don said is on target. The only question you have, right, is so basically, I don't know, J there is basically a Poisson process, right, in some way. So you have 2 parts though, right? You have this, and it tells you that it's going to be this. And then you have the minus version, right? Which is this. So I think what Don said is more or less on target, except that how do you handle, right? Or how do you account for the minus, right? Or what's the unifying approach that gets you there? What?
I will say for my guess, when it came to like finding like J0, it was just 0. But like if you do J1 minus, then that's also 0. So if you just keep on going from there, then we would
right. But my guess is this, that you would want to just to show that you understand what's going on with the symbol, and like you said, Don, right, it's exactly just a sum.
Yeah.
So let us be concrete and suppose that there are n jumps so far, right? There are n jumps so far.
Yeah.
So what is this? This will be the sum, right?
That should be the sum of like JG and like
Right? Where
the
you
count.
start from, yeah, you start from 0 to n.
Right.
And that obviously is n times n plus 1 over 2. Right? So that's the first one. The second one, right, because you do the minus part, that would be something like, I guess, because the first one doesn't count anyway.
Oh, the first one. Oh yeah, it does. Yeah, I see.
Do we agree? So that would be, right, obviously translating to, which would be n minus 1 times n over 2. Did I answer your question, Sharon?
Yes, that's it. And how about the part 2?
All right, part 2. Anyone cares to comment on that part?
I think I went over this with Tia yesterday. So he mentioned that it'd be better to, like, integrate XP itself and then rewrite like NS minus that in terms of like the count of n, and then once you get that, you integrate that again. But I'm not sure if that makes sense.
Okay, so all right, so let's see, right?
Wait, Don, I think you meant like for the first one you do the derivative.
Yeah, right. Yeah,
Yeah.
you find the derivative of xt, and then once you do, you integrate it back into xt.
All right, so let's try this. All right, I'm a very simple person. Let me just do something simple. In other words, right, you're dealing with this. Right. So it seems to me that there are two components. Right. That should be okay so far.
Yes.
Now let me ask you this. What do you think this component is?
This is the delta ns lambda.
To do these things, you have to visualize them a little bit, right? What are we doing here when we do this? Well, here's t, right? And ultimately, this is something like area under a curve. That's the Riemann integral. Area under a curve of what? Of this. What is this? This is 1 at some point, right?
Yeah.
It is 1 where exactly it jumps and is 0 everywhere else. So tell me, what's the area under the curve here?
A square.
Is it 0?
It's just zero. There's no area. Because, I mean, you have to draw,
Oh.
you have an area. So this is zero.
Mm.
But what is this? Isn't this the answer from part A?
Oh.
Right?
Mm.
Which should not be surprising this entity, right?
Mm.
Or if you want to
Yeah.
push understanding a little further, right? This is nothing but 1, right? DNS.
Mm.
Why? Because it's 1 when there's a jump, and it's 0 when there's no jump. So it's 1 DNS. What it comes out to? Does that make sense?
Makes sense.
Yeah, I see.
So I mean, like, again, I don't know what the TA said, and I'm pretty sure it's valid, but you know, after being so much time, spending so much time in this business, I see that fancy tools are appropriate in fancy, scenarios, right? If we need to differentiate, then yes, we differentiate. But sometimes, right, I mean,
Mm.
staring at the integral and try to see what the integral is telling you is a little bit more intuitive, I feel, and you might get an easier reason out of it. But valid. So
Oh. I see, and I know how to do the part 3. Thank you.
okay,
And also part 4.
so you're good.
But in this integral, it is 0 t 1 dns, not 0 1.
Wait, what question are you asking now?
In the integral, it is 0 t, not 0 1.
Yeah, sorry, that's a typo. Yeah,
Mm.
but it should be NT, right? So yeah.
Yes.
Any other question?
Oh, Professor, I sent you an email about like something about problem 4, which has something to do with the Python code. So I appreciate if you could check it out.
You just sent?
Yeah.
Okay, yeah. Otherwise, I don't think I received an email before.
Okay. Yeah. It's about problem 4 in the Python code. So
Yeah. Okay. Let me take a look.
yeah, I just wanted to let you know. But thank you.
Yeah, I'll take a look right now.
Professor, could I also send you my problem too? Because I'm like really unsure of like the math part, because I don't think like my integral, like fundamental theorem of calculus skills are very good. And I might have made like a really bad assumption, but I feel like I understand the procedure. I just don't think like some of the theorems I made were correct.
All right, fine. So hold on 1 second. So let's do this, right? Let's do 2 first, because it's just on the screen now. And then let me ask Dawn to share her screen and run the code, right? And we'll try to fix a problem there.
Okay, I think Dawn also left.
Oh, Dawn left already. Okay, fine.
Yeah, I'm just looking at the
I'll
chat.
just look at her. Okay, cool. So let's look at 2 for you, right?
Okay. I can also like share my screen if that helps. But I just have like a camera, so maybe it's better
No,
if I
it's fine. It's
really
fine.
walk through it
Because,
together.
I mean, I asked Don to share screen because you're asking code questions, but
Mm.
2 is a math question I can answer.
Yeah, I just like I think I'm having trouble. Like I have it in the I'm pretty confident in my integral form of the ZT that I solved, but I just like when I'm solving the integral because of the things inside of the integral, I don't know how to if I'm simplifying it right.
So again, right, as I mentioned in the email, you treat it like the Black-Scholes model, right? You
Okay,
treat it
yeah.
like Black-Scholes model. So here, ZT would definitely be 1 if you are between T and T1.
Yeah, now I see that.
And then would be, so we pick up a jump of size 1 plus sigma. So let's do this, right? 1 times 1 plus sigma times A1. If T1 less than equal to T less than T2. And then it picks up another jump of size 1 plus sigma square A1 times A2 if T1 less T2 less than equal to T.
Sorry, I'm lost. Why is it why is it A1 times A2?
Because the jump size is A2 for the second one, right? I mean, what you're given is the value of G. So G start at 0, and then it jumped to A1. So jump size is A1. Then it jumps to A1 plus A2, so jump size is A2.
Yeah. I'm just asking, like in the third equation you wrote like A1 times A2.
Yeah, because I mean, okay, if you want, it's gonna be 1 times
Oh,
1.
I'm stupid. It's rolling over from the past step. Sorry.
Correct. No, you're not stupid. It's just fine. It's, yeah, don't
My
worry.
bad.
No, it's fine. You understand? It's
Yeah,
just,
I understand.
so that's A. Do you agree?
Oh, that's the solution?
I'm sorry?
Oh, okay.
That is the solution.
Can I kind of explain how I did it and like if it makes sense? I'm not sure if it takes up like other
No, it's
people's.
fine. I mean, we're done with class, so people who stays want to stay. There's no time, no class left, right? I mean, we're done.
Okay. So
Uh,
like what I did was you gave us like the formula for ZT.
yeah.
And then like it's 1 plus that integral. So what I did was I broke up that integral into like T1, T2, like those time chunks
Yeah.
of the stopping times as the boundaries. And then I kind of simplified it. And the third integral I got to be 0, the one from T2 to T, because there's no change in G.
Okay. So
G.
yeah, that reflects the fact that right after T, this is just that.
Yeah.
Right? ZT basically is also a piecewise function.
Yeah, maybe it's better if I can just like briefly
You want to share your screen?
the thing is I didn't scan it just yet, but like
Oh, okay, that's fine.
maybe
But first of all, did you get this answer? Or you did get something different.
I didn't even get an answer. Like I got something that was like just a formula and then like a bunch of integrals and then I tried to solve the integral, but inside of my integral I had like a z s
So
minus.
also, right, Sherry, if you chase the integrals, that means you don't understand what's going on yet.
Oh,
Why?
okay.
Because I assume you do something like this. If I'm not wrong, you do 1 plus the integral, let's say 0 to t dgs for t less than t1, right? Something like that, right?
Yeah, sorry.
No, it's fine. But let me ask you, right? What is dg from here to here?
I bought A1 for that one.
No, hold on. We have to be very precise. Do you mean t equals to t1 or t less than t1?
Oh, so Okay, so it would be 0.
Yeah, because look at this, right? dg dg does not g does not change at all.
I
So
see.
yeah, so it's 0. That's why it's 1.
Okay.
Right? And then if you want, right, 1 plus 0 to 1, sorry, 0 to t1. Okay. Now what is dg at t1?
This should be A1. I
Correct.
think.
So that's why, right? So at t equals to t1, that's going to be 1 plus sigma, right? Times, but what's gs minus? 1, right? Times a1, right?
I just have a really like stupid question. What is the ZS minus? Like, what am I supposed to do with it?
The zs minus basically is the previous value before you jump, right?
Oh,
So
I see.
so previously, right, is 1. So it's going to be, do you understand?
Yeah, that makes my integral also make more sense because I had a bunch of those things and I didn't actually understand what it was doing. Yeah, it makes sense now because I think like the way that you've done it is kind of you start from it like.
Oh, but you know what? I think that actually says that my solution is wrong.
Oh wait, really?
Meaning that I should not have a parenthesis here. It should be this. It should be that actually,
Okay.
because
Oh, Drofan also agreed. In the chat. He
oh, cool, yeah, yeah. Please tell me, right? I just because I'm here doesn't mean that I I don't make mistake. All right. The reason is because you see that's your question, Sherry, right? ZS minus is 1 right before the jump at T1. So therefore, right, it's only this.
okay.
So that actually changed my second answer to 1 plus sigma A1, right, times
Wait, is this a plus sigma A2 or am I wrong again?
no, right? So let's analyze the second one, right? At t equals to T2, what happens? At t equals to T2, right? Basically, it's going to be, right, ZT minus, right, T2 minus, right, plus the jump at T2. That's what it is. That's ZT2. Do you agree?
Yeah. Yeah.
What is ZT2 minus? Well, before the jump is this. So it's going to be 1 plus sigma A2, right? What about the jump at T2? The jump at T2 will be sigma times the value before the jump. Sorry, A1, right? Not A2.
Oh yeah, I was confused again. But
Yeah. Times A2. So it's going to be
I
sigma
now.
A1 times 1 plus sigma A2. Yeah, that's the formulation. So that's ZT2. Jiofan, you agree? Yeah, did I got it right this time? Does that seem okay?
He says he has to think about it this time. I think I have to think about it too, but I will email you if
You
I.
have to think about it, okay? Because you agree with me here, so I suppose that you know the other one. But right, the principle is what? Just analyze it at the jump, right? This is always the case. What is the value before jump? You know it from your previous solution. What is the jump value? Well, this is the jump value. which is sigma times the value before the jump times the jump size. Right? And so there you have it. All right, think about it a little bit, but I'm pretty sure this is right now. Yeah. You know how to do 2? I mean, second part.
Well, I didn't even try it because I got stuck. Like I wasn't sure of my part 1 of that question, but I will try it and like probably if it doesn't make sense, I'll email you again.
Well, let me give you a hint. So it starts out at 1, but it has a dt component, right? So basically, the dt component says that zt is 1 plus integral from 0 to t zs ds up to t1, right? But what does that mean? That means that zt is e to a t. At t1, what happens? At t1, zt1 is zt1 minus plus delta zt1, right? What's zt1 minus? Well, it's this. So it's just e to t1. Plus, what's delta zt1? Delta zt1 is sigma e to t1 times a1. So it's going to be e to t1, 1 plus sigma times a1. Then from t1 to t2, what does it do? It follows the same formula. So you can check that it's going to be just e to the t, 1 plus sigma a1. And then at t2, and then after t2, like that. Does that make sense?
Okay, yeah, I think I'm seeing it. I think the main like reason why I was having trouble is because I wasn't building it up like incrementally. I was just trying to like solve it just like everything, looking at everything from the same level rather than like starting from the lower time points and then building it up.
Right. I think you need to build it up a couple times like this, and then because it's the same way, if it builds up the same way, then you get a pattern, right?
Yeah.
But the pattern is what? Basically, the pattern is going to be a multiplicative jump discontinuity, right? Basically, the message here is at every jump point, you pick up a multiplicative jump size, right? Before, because we have a Poisson process, these guys are always 1, so they don't show up. Now we have a non-zero jump size, so we get this. But that's it, right?
Yeah, thank you so much. I think, yeah, I know where my thinking was off now.
Hello, Professor.
Yep.
I would like to ask in the part 3 and part 4, in the problem 3, how to use the condition of the expectation to prove that it is or is not a martingale.
For part 3?
Yes, how to prove that it is a martingale?
Hold on. So, right, so you follow the hint and just break it down to 2 and then use part 1 of the problem. Yeah, okay. So let's do it, right? So part 3, basically, I'm trying to think. Yeah, basically, right, part 3 says that yt, right, which is going to be 0 to t after the hint.
Yes.
Minus this. This will be, right, by part 1, you got this to be nt times nt minus 1 over 2, right?
Yes.
Minus the,
Yes.
okay?
Okay.
And so now you want to condition, right? You want to condition. So you want to take conditional expectation. So you want to take conditional expectation. Let's say y sub u condition on ft, right? That's what you want.
Yeah.
And you want to have y of t come out. Okay, you want the yt to come out. So, well, what do? You plug in this expression. So you got, right, and u, n of u minus 1, right, over 2, minus the integral from 0 to u of lambda n s minus es, condition on ft. Okay, that's plug in the formula. So now you use the hint that says, so you have 2 parts to take care of, this part and this part. Okay, so let's take care of the first part. So what is this? So you got n squared minus nu over 2, right? Condition on ft. Well, I have nothing better to do but, you know, the trick of like and subtract. So I got n, right, u minus nt plus nt squared, right, divided by 2, and then minus, right, nu minus nt plus nt divided by 2, condition ft. Okay, all right, so I will, right, square this and then, you know, basically use the independent increment property, which will give me expectation of nu minus nt squared over 2 plus nt squared over 2, and then plus, rather minus, right, nt over 2, and then minus, right, expectation of nu minus nt over 2. Is that okay? That's after I decompose this piece and this piece, and then use the independent increment. So this is the expectation of the square of a Poisson, which is the variance plus expectation square. So that will be, the variance of Poisson is lambda, right? So this is going to be lambda times u minus t. Oh, sorry, right? This is this. These guys are just by themselves because they have no expectation. This plus, so 1/2 outside, right? Plus expectation of the square, which is lambda square, right? Like this. And then this is lambda. So this subtract this, right? Gives you 0 actually. Okay, and then you got n squared t minus nt over 2. Is that okay? So that's the first term. That's this guy. Now we take care of this. This will be so as the problem mentioned, is integral from 0 to t ns minus ds, and then plus, right, lambda integral from t to u of expectation of ns minus condition on ft. And for one thing, right, we can drop the minus because this is integral with respect to dt. So Riemann integral, right, doesn't care if you have left, right, or middle point. Well, this will give us ns minus ds, and then plus, right, expectation of ns given ft will be lambda times nt plus lambda times s minus t ds. Okay. Which will give you times nt u minus t, and this is going to be lambda square u minus t square over 2. Question? All right. Everything looks good except that if this is a minus, then it would work. Somehow it becomes a plus, because basically you see this cancel with this. I expect this to cancel with this too. Oh, it's a minus, right? Because you subtract this. You subtract this. Yeah, good. So you subtract this. So basically, look at the top terms, right? So basically, when you subtract, you got this cancel with this, okay? And then you got this cancel with this, right? Anything else? So, hold on, this is no plus, right? Yeah. What about this term right here? So after subtraction, what you should have is nt times nt minus 1 over 2, all right, minus lambda from 0 to t ns minus ds. Which is perfect, except that I have this term right here. Because, you know, this and this together is exactly the integral from 0 to t of ns times dns minus 1. Sorry, ns minus, like that. Minus lambda t. Lambda s. Okay. You use part 1 again to bring this back into here, right? You bring this back into here, and then this absorb here. So that's exactly almost what you want, right? Because like this, except that somehow I pick up this extra term. It should not be there, and that's where I'm a little bit confused. That's when, by taking this at conditional expectation, I don't know where this goes. Maybe I missed the cross term here. Yeah, I dropped a cross term here. Oh yes, I dropped a cross term here. I made a mistake. So basically, right, when I go from here to here, basically there's a cross term of the square that does not cancel. The cross term exactly gives you plus 2 lambda u minus t times nt divided by 2, which exactly cancel and gives you subtraction with this term. Okay, so they cancel and give you that. Does that make sense? Or not so much? The point is you just have to compute this conditional expectation. And it has so many terms, so that's why I have to write it down like that. But it is pretty straightforward in terms of like what you need to do about the decomposition. Sharon, you okay? Anyone?
Okay, okay. Thank you.
All right. Any other question? All right, so I upload this, right? So whatever I wrote here, you will have it when you solve the homework. So you can trace my calculation again.
Yeah, thank you for walking through it. I think Joafan has a question in the chat.
Somehow I think he only messaged you. I don't see any chat here. Did he send you a private message?
No, it's not. It's not to me. It's to everyone.
How come I don't see any chat showing up?
He's asking about the first question and problem.
Oh yeah, that's true. Sorry, Joafan. I did not try to ignore you. Somehow. Oh, and yeah, somehow the chat doesn't flash up for me. You don't understand how to find the volatility. Well, you have to understand what the definition of volatility is. Okay, what's the definition of volatility? That's the question I asked you on day 1, right? So definition of volatility is something like the rate of the variance, right? So it's going to be a square root of variance of the log return divided by t, right? Because this is the rate of the variance per unit of time. When you take the square root, you get the standard deviation. And so that's the volatility. Agree? So it's a unit of the variance, a square root, right, of the variance rate. Well, so if you have your model to be dst, right, is rst dt plus sigma st dwt plus gamma st minus, right, dnt minus lambda t, right? Okay. What is your log return? What is your log return? Right. So your log return will be, right, if you remember the formula for your stock price, right? Your log return. Oh, so first of all, right, what is your log return? What is your log price? Your log price, right? Log st, as you can solve, will be log of s0 plus r minus 1/2 sigma square, right? Times maybe let's do this, right? Minus gamma lambda tilde times t, and then plus sigma times w tilde t plus gamma times, hold on, log, right, of 1 plus gamma times nt. Is that okay? That's your log return. Oh, so that's your log price. So your log return, right? Your log return will be yes. So what's the variance of this? Well, so it will be, right, the variance of this plus the variance of this. So it will be, right, I hope I'm not wrong here. Somehow, so I think maybe the question I asked you is slightly wrong. Sigma squared times t, right, plus lambda log of 1 plus gamma square times lambda times t. Right. So that will be sigma squared plus log of 1 plus gamma square times lambda times t. So what's your volatility? Your volatility is the square root of this. Okay. Now, what I said, right, I think in the problem is only gamma square, right? Instead of log of 1 plus gamma square. I have a defense for that. So this is the correct one. But my defense is if gamma is small, which, right, most of the time we have, then log of 1 plus gamma is approximately gamma. That's why I wrote that way. Is that okay? Oh, I see. Yes. So my mistake, all right? It's really my fault. But the reason why, you understand, the reason why I write this is because of the approximation to the law. Okay. But yes, I should be more careful. So I will fix that. Okay. Any other question?
Oh, sorry, this isn't related to like this homework in particular, but you said we would have homework during spring break. Would it be possible to like have like 2 times the amount of homework but due when it's like when we're back to school? Like would it
It's always due when you're back to school. Don't worry, I will not ask you to turn in the homework. I'll even make you a better deal. I'll give you the same amount of homework due when you get back to school. Is that okay?
Oh, okay, thank you. Yeah, just because like I already made plans with
No,
my
no.
family
You
to
take your time on spring break. I'm not gonna impose like, you know, you have to do work on spring break or anything like that.
Oh, okay, I was just afraid that we had homework due next Wednesday, and then I was okay. Thank you. Yeah, thank you so
Okay.
much for going over
Yeah,
the.
no problem. Johan, I don't think gamma is 0, right? Gamma is not 0. So the mistake I made, right, is that, oh, I see. Because you say when gamma is equal to 0, so they are equal. Yeah. But yeah, there is this approximation that's very popular, right? But I should not do that. I should just use this and then maybe tell you that this is the approximation you're meant to use. Okay. Any other question? So I'll fix that. Thank you, Johan, for pointing it out. Okay, I'll fix the homework. All right, guys. Thanks for staying. I hope I addressed most of your questions. Have a safe spring break, and see you in 2 weeks. Yeah, thank you.